The two most prominent functions for numerical calculus in the Wolfram language are nintegrate, which does numerical integration, and NDSolve, which solves differential equations. Starting with numerical integration, this shows nintegrate giving a numerical result for a simple integral. The first argument in nintegrate is the integrand, and the second argument gives the integration variable and the range of the variable. Nintegrate can also do multidimensional integrals. For example, this shows an integral in 3 dimensions. The range of integration can also be specified as a geometric region. For example, this input gives a region corresponding to 1 quadrant of a unit disk, and this uses nintegrate to do a numerical integral over that region. The NDSolve function solves differential equations. For example, this shows NDSolve computing a solution to an ordinary differential equation. The first argument in NDSolve is a list of equations and conditions. The second argument gives the function to solve for, and the third argument gives the independent variable and the range of that variable. The single quote mark in the equation is the notation for a derivative. The result uses an interpolating function expression, which is how NDSolve represents the solution. The solution to a differential equation is a function, and NDSolve computes points and derivatives along that function and returns those points and derivatives inside of an interpolating function expression. The interpolating function expression can be used as in this input to give a value of the solution function at any point in the range of the solution, and this gives a plot of the solution. Interpolating function expressions provide a convenient way to get values of the solution anywhere in the range of the solution, not just at the points that were computed by the numerical differential equation solver. Also, the result from NDSolve is a list of solutions, and each solution is a list of rules. Usually from NDSolve there is only one solution, and in this example that solution consists of only one rule, but for consistency the list of lists structure is used even when there is only one solution or only one rule. For situations where it's more convenient to have just the solution function, there is a function called NDSolve value that works like NDSolve and computes the same solution but returns only the interpolating function expression rather than a list of lists of rules. NDSolve can handle several other types of differential equations. That example is an initial value problem. This shows a different type of problem called a boundary value problem, where boundary conditions are given at both ends of the range of the solution. And here's a plot of the solution. NDSolve can also handle many types of partial differential equations. For example, this shows NDSolve giving a solution for a simple partial differential equation. This input uses many of the same notations and the same structure as the input for an ordinary differential equation, the main difference being that for this partial differential equation there is more than one independent variable. To accommodate the additional variables, derivatives are entered using derivative expressions, or derivative expressions constructed using the d function. The notation used earlier with single quote marks to indicate derivatives works for functions of a single variable. Derivative expressions are more general and can be used to represent derivatives of functions with any number of arguments. The equation in this example is a one-dimensional diffusion equation or heat equation, which physically could describe diffusion or the movement of heat in one dimension. This input uses animate to plot that solution as a function of the position variable x and with the time variable t as the animation variable. The solution in this example could represent diffusion or the redistribution of heat as a function of time. There are several functions and tools to make it easier to enter common partial differential equations. For example, this input gives a solution for a partial differential equation called Laplace's equation in 2 dimensions. The range of the independent variables in that input is given as a geometric region, which was set up using the region function. Also, rather than using explicit derivative expressions, this input uses the Laplacian function, which represents the Laplacian operator from mathematics. The Laplacian operator is a sum of second derivatives. The same sum could be entered using derivative expressions, so the Laplacian function is just a convenient tool for getting that result. Also, rather than explicit equations for the solution on the boundary, those conditions are entered here using the Dirichlet condition function. Mathematically, a Dirichlet condition is a condition that gives the value of the solution on the boundary. Here is a plot of the solution. Physically, this solution could represent electric potential or steady-state temperature in a region. Beyond these basic examples, both NDSolve and NIntegrate support broad systems for controlling what these functions do. For NIntegrate, this system is described in links from this page on Advanced Numerical Integration in the Wolfram Language. These notes include a detailed discussion of the mathematics and the algorithms used in NIntegrate and suggestions and examples related to improving the performance of NIntegrate primarily through option settings. These notes are quite extensive and the details will not be explored here, but as a simple example of the sort of things that can be done, consider this integral where NIntegrate quickly returns a correct answer. That shows the default behavior of NIntegrate with all of the default option settings, but the same answer can be computed more quickly, at least in this particular example, by choosing a non-default value for the method option. The difference in speed can be seen using the repeated timing function, which shows that the input with the non-default value for the method option is a little bit faster in this example. The integrand in this example has a singularity in the range of integration, and an even larger improvement in speed can be achieved by including the location of that singularity in the specification of the range of the variable. Still more improvement in speed can be achieved by setting the symbolic processing suboption to 0, which sets the time to allow for symbolic processing to 0, which effectively turns off the symbolic processing that is normally done by NIntegrate. Although NIntegrate is primarily a numerical function, symbolic processing is used by NIntegrate for a variety of purposes, such as in this example, choosing a method of integration and finding the exact locations of singularities. The default value of the method option, for example, is automatic, which causes NIntegrate to use symbolic methods to choose a suitable method for a particular integral. In that last NIntegrate input, however, where the method is specified explicitly in the method option and the location of the singularity is included in the range of the variable, this symbolic processing is not needed and a small improvement in speed can be achieved by turning it off. In general, however, that symbolic processing can be very important. For example, if symbolic processing is turned off and the location of the singularity is not specified in the range of the independent variable, then NIntegrate for this integral does a very large number of evaluations, trying to locate the singularity numerically. The calculation takes much longer, and the evaluation eventually generates a few warning messages and returns an incorrect result. Another way of assessing the performance of NIntegrate other than checking the speed is by counting the number of evaluations of the integrand, which can be done using the evaluation monitor option. For example, this gives the number of evaluations used for the default handling of this integral. And this gives the number of evaluations needed with the non-default value for the method option. The value of the evaluation monitor option gives an expression to evaluate for each evaluation of the integrand. Here, that evaluation increments a variable k so that the final value of k gives the number of evaluations. Like NIntegrate, there are similarly extensive and detailed notes for NDSolve, which can be found by following links from this page on Advanced Numerical Differential Equation Solving in the Wolfram Language. This documentation includes mathematical background and typical applications using NDSolve for various types of ordinary differential equations, finite element methods, and the numerical method of lines for solving partial differential equations, methods for handling boundary value problems in differential algebraic systems, and so on. In most cases, the appropriate method for solving each type of problem is chosen automatically. For example, this input includes both differential equations and algebraic equations, so this is a differential algebraic system, and the differential algebraic equation solver is used automatically. And here's a plot of the solution. For another example, this partial differential equation, which is the equation shown earlier, is solved using a finite element method. Finite element methods involve constructing a mesh over the range of the solution and solving the differential equation in each element of the mesh. This shows the mesh that was used in this example. The method that was used in that example was also chosen automatically. For applications where it's useful to specify methods or to set non-default characteristics of methods, it is possible to do that using options. For example, here is a modification of the previous example where the method option is included to set a parameter that comes up in the construction of the mesh. The effect of that change in this example is to use a finer mesh, which could, in principle, lead to a more accurate solution. The advanced documentation describes the mathematics and features of all of the methods that are used by NDSolve and includes many examples of how those features can be controlled. Before getting to the advanced documentation, however, more basic information about NIntegrate and NDSolve can be found in the sections on numerical integration and numerical differential equations in the tech note on numerical operations on functions. Another useful reference specifically on applications of partial differential equations is this page called PDE Models Overview, which includes extended examples from acoustics and electromagnetics and structural mechanics and other areas of application.